So now we know how to approximate our integral. But anytime you're approximating something, you really want to know how good is your approximation. If it's not even close at all, then you really don't care, right? You want a good approximation. So what we want to do is we want to ask ourselves question, because we like to talk to ourselves. Question, how good are these estimates? From how close are they to the exact value? So another way to rephrase this question is say, what is the error in using this as an approximation? How error refers to how far off we are from the actual value, the exact value. Okay? So let me tell you, I can't tell you the exact error, but there is an upper bound on this error. Okay? So I'm going to call this error bounds. In order to get this upper bound, you need to know something about the second derivative of your function. You need to know a bound on it, this k, and this k, let me tell you, it's just a constant, okay? We'll do an example in just a minute where I help you find the value of k, okay? For x between a and b. Okay. And we're only going to concern ourselves right now with the error for using the trapezoidal rule and using midpoint. Okay. So if I'm going to call E of t the error for trapezoidal and E sub m the error for midpoint are the errors for maybe not say 4, say n, the trapezoidal rule, and midpoint rule. Okay, let me tell you what the bound is. The absolute value of E of t is less than or equal to k times b minus a cubed over 12n squared. And you're bound for the midpoint rule. It looks very similar. The only difference is the constant has changed in the denominator. Em, it's k times b minus a cubed over 24n squared. Again, we don't know the error exactly, but I know how the biggest that it could be, okay? Which is as good as we're going to get here. So let's take this and calculate our error from the last examples, okay? Let's use this to calculate the error from the previous example. Okay. So in order to do this, I told you had to know something about the second derivative. You needed a bound. So let's start with our function being, right, in the last examples we were looking at 1 over x. What's the second derivative of that? Think of that as x to the negative first.
6x to the negative
just the second derivative. So just take, oh, sorry, yep. I see what I did. Let's start with the first derivative. I was trying to make you do too much at once. So the first derivative, this is x to the negative first. So it'll be negative 1 over x squared, right? And then now we want to take the second derivative. So think of this as being negative x to the negative second. It'll become a positive 2 over x cubed. Yeah. So I need to know how large this can be in my interval that I'm looking at. Remember, I'm looking between 1 and 2. So I'm looking between, we said x was between 1 and 2. So let's look at our second derivative here. Well, first thing, this is positive, right? When x is between 1 or 2, this thing is positive. And I want to say how big this can get, right? I want to say the largest value it can be. X only appears in the denominator. So if I want to make the value as large as possible, I need to make that x as small as possible. Because it's in the denominator, a small number means you have a bigger number, right? So what's the smallest x can be? 1. So this is less than or equal to 2 over 1 cubed, or 2. So that's going to be my k value that I have in my problem, okay? That's my bound on the second derivative that I needed, okay? All right, so now we know k was 2. Our beginning of our interval was 1. The end of our interval b is 2. And n, in our previous example, n was 5. Okay? So now we can check what is our trapezoidal error using that approximation. It was k, which is, so maybe I'll write down the formula.
Why did you plug in the 1 for x?
Because
How'd you know to do that?
my goal was to make this 2 over x cubed. I wanted to make it as large as possible. The 2 in the numerator is fixed, so the only thing that's changing is the denominator. I want to make that number as big as possible, but because I have x in the denominator, I need to make x small.
Okay.
Because a smaller number in the denominator gives me a larger number
So
overall.
you picked the smaller number out of the two
Mm-hmm.
x's. Okay.
Out of the range, Yeah. So kb minus a cubed, and it was 12n squared. Okay. All right, so we now know all of the values here. So k was 2. 2 minus 1 cubed over 12 times 5 squared. So if you simplify this, you're going to get 1 over 150. And if you put that in a calculator, this is approximately 0.00667. So your error is no bigger than that number, okay? Which to me means you're pretty close to the exact value, right? You're pretty close, up to 3 decimal places. Yep. Oh. 12 times, but there's a 2 in the numerator. Yeah, so it'll cancel to give you 150. Yep. Yeah, you're good though. Other questions?